Thank you. You are welcome to Trinity Mathematical Clinic. I am your host today, and my name is Mega, and I remain Mega. So today we are going to be looking at integration by parts, which is also referred to as integration of products. That simply means that there are cases whereby we would have to integrate the products of functions. It can be two, it can be three, it could even be more. But we are only going to be looking at the integral of the products of two given function. Now, the integral of the integration by parts is said to be the process of finding the integral of the product of functions in terms of the integral of the product of their derivative and their antiderivative. I don't know if this actually makes sense to you, but I hope it does make sense. Now, the integration by parts is usually given an equation or an expression, a mathematical expression, to be given as the integral of u, the v, is equal to uv minus the integral of v, the u. Now the question is, how were they able to generate this particular relation of integrals? Because this is what we are going to be using in finding the integral of the product of any given function. So how did they get this? Now, to generate this in your own terms, we can actually begin by assuming any particular function. Pick twin functions. Let's say you have u and you have v. Multiply them together. What do you get? You get uv. If you differentiate this function, the derivative of uv, what do we get? Let's say we have v, the x, representing the derivative of something, but in this case, uv. So when we differentiate two functions that are multiplying each other, by the product rule, we have that to be given by u, the v, the x, plus v, the u, the x. Take notes. The reason for this is so that we can be able to get back this given equation or relation. So with this now, what do we do at this instance? We can integrate both sides of this equation. If we integrate both sides of this equation, we have this to be given by the integral of v, the x, of uv with respect to x is equal to the integral of u, the v, the x with respect to x plus the integral of v, the u, the x with respect to x. So this is what we have here. From the left hand side, take note that the left hand side is the integral of a given derivative. So what you're having here is the opposites of each other. You are integrating a derivative. If you integrate a derivative, you get back the original function. So what that simply means is that, suppose we have x raised to the power of 2. When you differentiate this function, what do we get? We get 2x. How do we get back 2x? It is when we integrate it. When we integrate 2x, we should have this to be given by 2x raised to the power of 2 all over 2, so that this cancels out this and we get back the original function. So when we integrate a certain derivative, we get back the original function. So it means that the integral of the derivative of uv with respect to x is going to give us the original function uv. So this given by uv is equal to the integral of u, the v, the x with respect to x plus the integral of v, the u, the x with respect to x. So what do we need to do here? We can rearrange this given equation such that we make this a subject. If we do that, we have this to be given by the integral of u, the v, the x with respect to x is equal to uv minus the integral of v, the u, the x with respect to x. And this is usually simplified into the shorthand expression to be given by the integral of u, the v, is equal to uv minus the integral of v, the u. So this is what we would actually need whenever we are to integrate by parts. So from the left hand side, we have here to be given by u. U is said to be a given function. Any given function. and the v is representing the derivative of a certain function. And if you look at v here, v is said to be gotten by integrating the derivative, that is the v. So we're going to see how we can actually do that by following the steps that has been outlined here. That whenever you are to integrate the product of two functions, you must know your u and you must know your v. So from the given process here, we have here to be, first thing, choose your u and choose the v. Then the next thing for us to do is to differentiate u and integrate the v. So when you know your u and you get the v, you integrate, you differentiate u and you integrate the v. Let's look at this example. Let us see how we can actually do that. Now, the first part of this example is given by I. So we have that the integral of x exponential x with respect to x. This is what we want to integrate. Now, if you look at this is x multiplying another function, exponential x. The question is, what should be our u? Should our u be x or should our u be exponential x? Now, there are some methodologies that are outlined or given in order to appropriately select the u function and the v function. So in this case, we are going to be picking our u to be given as, we have to choose, say, let our u be equal to x and the v, because we need to select the v, picking out our v, the v. So the v is equal to exponential x. So what do we do at this point? We differentiate u and integrate the v. If we differentiate u, we have here to be given by the derivative of u with respect to x is equal to 1, such that according to the formula, we would need to get du. This is given by du. We would need to get du. So when we make du the subject here, we have that du is equal to 1 dx, and that is simply dx. Now, when we come to the v, what do we do with the v? According to the steps here, we have to integrate the v so that we can get v. Integrating this derivative dv so that it enables us to get the function v. So in this case, we have here to be given by v is equal to the integral of this derivative, the v. And this is simply the integral of the v is given by x here. We have that to be exponential x. So therefore, we have this to be given by v is equal to the integral of an exponential function with respect to x gives us that exponential function, depending on what the coefficient of x is here. So, but the coefficient of x here is 1. So when we integrate this exponent, we have here to be an exponential function. Nothing does change. So now that we have gotten for all the needed parameters for the given for the given formula in integration by parts, we can now substitute. Now, substituting. What are we substituting into? Into the integration by part formula. So substituting, we have the integration by part formula to be given by the integral of u, the v, is equal to uv minus the integral of v du. Now, when you come to the left-hand side, we want to begin our substitution. We have this to be given by the integral of u is given by x. So we substitute, we have that to be x. The v is exponential x. So we have this to be exponential x. Integrating all this with respect to x. And this is equal to u is x. So we have that to be x times v is given by exponential x. So we are substituting. We have this to be given by exponential x minus the integral of v remains exponential x. We have that to be exponential x, and the u is given by 1 dx. So we have this to be times 1 dx. So we begin by saying this is equal to x times the exponential x. We have that to be x exponential x minus the integral of exponential x times 1 gives us exponential x with respect to x. So that we have this to be x exponential x minus if we integrate an exponential function, it gives us that exponential function. If there is no power attached, if there is no coefficient attached to x except probably 1, so we have this to be exponential x. And remember that the integrals we are working with here is the indefinite integral, so we have to introduce a constant of integration, so plus c. Hence, we have that the result to this given integral x exponential x with respect to x is equal to what is common between these. We have that to be exponential x. When we factor that out, we have exponential x of exponential x into this, that is x exponential x divided by our factor. We have here to be x exponential x divided by our factor minus 1, and that is plus c. So this is how we can apply the exponential function. And like I did mention, there are certain rules that are already laid down that enables us to know how to choose our u and what our dv function should be. So let's look at this other example and see what this should bring us to. So now we are going to be working with this second example now. It remains the product of two functions. The first factor is x raised to the power of 4, and the second is already a log function. So, my friends, what are you going to choose as your u function? Should our u be x raised to the power of 4, or should our u be the natural logarithm of x? Well, before you can choose this, first and foremost, take note that whenever we are picking our u functions or our dv functions, let us assume that u is said to be the first factor, x raised to the power of 4. Remember, u has to be differentiated, and if the v is a log function, so that we have this to be a natural logarithm of x, we differentiate u and we integrate the v. Remember that if we try to integrate the natural logarithm of x, you might not really get a result because there is no standard integral for the log of a given function, but there is a standard result for the derivative of the log of that function. So it means that since you cannot get the result for integrating the natural logarithm of x, what do? We would have to change over by giving u the log of x and the v the exponent, the powers of x. So we'll come to this now by saying that first, our choice of u is based on the fact that we cannot integrate the natural logarithm of x. We cannot integrate this log function. And the v is equal to the second factor, which is x raised to the power of 4. So this is what we do now. So we should know how to choose our u and also for the v. Now at this instance, what do? We differentiate u and we integrate the v. So differentiating u, we have the u, the x, is equal to 1 all over x. So that we have that the u is equal to 1 all over x dx. And when we come to the v, it's already a derivative. You don't have to differentiate it. In this case, we integrate it. So when we integrate it, it gives us back the original function, v. So with this, we have v is equal to the integral of the v, and this is equal to the integral of x. The v is x raised to the power of 4. Only substituting, we have the integral of x raised to the power of 4 with respect to x. So that we have here to be given by v is equal to, if we integrate this, we have that to be x raised to the power of 5 plus x raised to the power of 5 all over 5. Now, in this case, we do not have to have the constant of integration because at the end, we are actually going to introduce that, but not in this case. So now that we have gotten for this now, the next thing for us to do is to substitute. Substituting into the integration by part formula that is given. So given that we have substituting, we have the integral of u the v, is equal to uv minus the integral of v du. Now when we substitute, we have here to be given by u is given as the natural logarithm of x, and the v is said to be given by x raised to the power of 4, the v times x raised to the power of 4 done with respect to x. And this is equal to u remains the natural logarithm of that, the natural logarithm of x, and v is x raised to the power of 5 over 5. So we have it to be x raised to the power of 5 all over 5 minus we have this to be given by minus the integral of v is x raised to the power of 5 over 5, x raised to the power of 5 all over 5, and du is given by 1 over x dx times 1 over x dx. So from the left hand side, remember that we can also rearrange these given functions. We can rearrange these given functions to suit the position, the arrangements they initially were. Why? Because it is said that multiplication is commutative in the sense that a times b is the same thing as b times a. So rearranging this, we have this to be given by the integral of x raised to the power of 4 times the natural logarithm of x with respect to x is equal to, this multiplies this can be rewritten as x raised to the power of 5 over 5 times the natural logarithm of x minus, in this case we have here to be given by, we have this, please take note that there is a denominator of 5 here. We can factor out this constant out of the integral so that we have this to be 1 over 5 of the integral of this times this is going to give us x raised to the power of 5 all over, the denominator is x with respect to x. So we have this to be given by the integral of x raised to the power of 4 of the natural logarithm of x with respect to x is equal to x raised to the power of 5 all over 5 times log x minus 1 over 5 of the integral. This cancels out one of these and we have here to be given by 4. So we have this to be x raised to the power of 4 with respect to x. And this is going to be equal to x raised to the power of 5 all over 5 times the natural logarithm of x minus 1 all over 5. And we have to integrate x raised to the power of 4. And that is given by x raised to the power of 5 all over 5 plus the constant of integration. So in all of this now, we can actually see similar terms between the first term and the second term, where we have x raised to the power of 5 over 5 and x raised to the power of 5 over 5. So our factorization is an x raised to the power of 5 over 5. So we have x raised to the power of 5 over 5, open brackets, the natural logarithm of x minus 1 all over 5 plus the constant of integration, and this gives us the final solution to that. So thank you for watching, and I hope you do enjoy this. So please, thank you.